Hello, my name is Mr. Stabner, and this is a lesson in logarithms, a four-part series detailing all the different aspects of logarithmic expressions, functions, and equations. In this first part, we will be graphing exponential and logarithmic functions and analyzing each of their graphs. So what even is a logarithm? A logarithm is an inverse of exponents. We already know that exponents are just repeated multiplication. 2 times 2 times 2 times 2 is 2 to the fourth. Well, 2 to the fourth is 16. As such, the logarithm at that base of 2 applied to the number 16 becomes 4. Same with 5 raised to the negative second power is 1 over 25, 1/25. The logarithm at base 5 of that fraction 1/25 is negative 2. So anything we've done with exponents can be described using logs. Okay, so let's actually start graphing some of these functions. Now, for a couple of the easier ones, I'm going to live draw them so that you can see step by step how you would even do those things. But ultimately, you are just taking x values, putting them into functions, finding the y values, plotting points, graphing lines. Pretty standard. So if I take a look at this first function, f of x equals 2 to the x power. Putting in the x values of negative 1, 0, 1, and 2, I get y values of 1/2, 1, 2, and 4, which allows me to plot a few points on my graph. Negative 1 is 1/2, 0 is 1, 1 is 2, 2 is 4. Now, if you look at this function, you might notice that over on the left side, it seems to be trailing closer down. In fact, if you were to keep looking at the function and get more values, you would see that it almost hits the x-axis. And on the right-hand side, the function is going to continually increase infinitely big. Next, if we look at a function whose base is 1/2, putting in exponents of negative 2, negative 1, 0, and 1 is going to give me y values of 4, 2, 1, and 1/2. So for those x and y coordinates, negative 2 gives me 4, negative 1 gives me 2, 0 and 1, and 1 is about 1/2. At this point, you might recognize that a similar thing is going to happen with our second graph, but instead of my line going from a flat curve on the left to a slope increasing up, it has reversed. So my graph actually curves down and almost hits the x-axis on the right, but curves up and gets infinitely big on the left. Now, the first function is increasing because its base is larger than 1. The second function is decreasing because its base is a number smaller than 1. Let's dig a little deeper. The graph is already set up for us this time. Our function is 3 raised to the x plus 1 power. But we're going to look at domain and range, end behavior, intercepts, and asymptotes. Knowing what you know about functions already, I want you to pause this video and see how much information you can write down related to this function before I remove my dorky little spoiler cards. So what did you come up with? What intercepts did you see? Asymptotes. Well, I do see that it does cross the y-axis at 3, but it doesn't really look like it crosses the x-axis. It kind of looks like it's sitting there. In fact, there is no x-intercept because that's where a horizontal asymptote is currently living. Now, how does that affect our domain and range? Well, if there is no vertical asymptote to speak of, then our domain is free to roam. But the horizontal asymptote is going to affect our range. Because my function is forever decreasing and my function is forever increasing, my x values go from negative infinity to positive infinity. But because my function is balancing just on top of the x-axis, my range starts at 0, but it still goes on forever to infinity. This range is what's going to take care of our end behavior. Because our x values can go on forever to negative infinity, our function has to go somewhere, and our function does go to 0. And because our function can go all the way to positive infinity, our function also gets to go all the way up to infinity. Let's do another one. Again, we're going to use the base of 1/2, but this time we're going to take the function and subtract 4 from it, giving us this table of values and the graph that you see. Again, I want you to challenge yourself by pausing this video and referencing what the example number 1 was talking about to see if you can fill in all of the information underneath my dorky little spoiler cards. There is most definitely an x-intercept here at -2 and a y-intercept here at -3. Again, we don't really see any vertical asymptote. There's no real spot on our graph that shows that. But there is definitely a horizontal asymptote at -4. As such, we have similar domain and range and end behavior as the previous example, but this time the range is starting at -4 instead of 0, but we still have negative infinity to positive infinity x's for our domain, but this time the -4 from our range belongs to when the x values are increasing instead of decreasing. So if we examine logarithmic functions, we're really just doing an inverse of exponential functions. This log base 2 right here is really just talking about what happens when we take 2 to an exponent. What are we actually working with? So if I take these y values, we're going to get the same numbers we got before, but now they're going to be x values. So 0.5, 1, 2, and 4. So our graph is going to have 0.5 at -1, 1, 0, 2, 1, and 4, 2. So our curve looks similar to what it did before with exponentials, but now my function is going to live just to the right of the y-axis. So looking at this function on the right, we have a base of 1/2. So its inverse is similar to our earlier example. So if I take our y values from this table, put them into the equation, 4, 2, 1, and 1/2 become our x values, which gives us a slightly different look to our graph than before. But it has a similar shape to the other three graphs. So my function is still only getting close to the y-axis, but it is going to curve downwards. So just like before, when our base is larger than 1, we have an increasing function. When the base is smaller than 1, our function decreases. So let's finish up this first video by looking at two final examples. Two logarithms that are the inverses of our previous examples in this video. Once again, challenge yourself. Pause this video and see if you can identify what the domain and range, the end behavior, the intercepts, and the asymptotes are, and then we'll briefly go over all four of them. This time, our function has no y-intercept because there's a vertical asymptote there, but there is an x-intercept. So because of that vertical asymptote at 0, our domain can never actually touch 0. It can only be close to it. But our range doesn't really care. Our range is from negative to positive infinity. That's really why our end behavior has both negative and positive infinity in here. But here's the main change. Our function can't actually ever be left of 0. It can only approach 0 from the positive side. So that little change is what happens with logarithms. There's going to be a starting point. 0 is our starting point. We just can't use it. So that's why we have this little notation of a plus sign. Our function can get close to 0, just not at 0, but only from the right side. Alright, final example. We have a logarithm. It has a base of 1/2. This time, x plus 4 is on the inside. Last round of challenge questions. See if you can figure out what's behind the spoilers before I reveal them. Go ahead and pause the video. So this time, we do have an x-intercept at -3, a y-intercept at -2, but our vertical asymptote seems to be at -4. Our function cannot ever get to -4, it can only get close to it. So our domain ends up being from -4 to positive infinity. Range is from negative infinity to positive infinity. But because our function cannot ever touch 4, can only approach it from the right side, our limit, our end behavior, does go to infinity. But when our x values are increasing, our function's actually decreasing to the bottom. Thanks for watching, and I hope you found this video at least a little bit informative about the relationship between exponentials and logarithmic functions. Have a nice day.